En nu streamt hij wel. En nu ben je gemute.
Ja, ik zie het, sorry. Ik hoef niks meer te veranderen nu, hè?
Nee, nu is hij als het goed is live.
Ja. En dit heeft een URL die we ook gewoon op Twitter kunnen zetten, bijvoorbeeld. En dat is, even zien.
tv.nikhef.nl.
Ja, precies. Oké, dan doe ik dat nog even. En dan kunnen we zo beginnen. Als we onze spreker tenminste krijgen. Maar goed, dat komt nog wel. Goedemiddag allen. We gaan zo naar Engels, maar even in het Nederlands. We hebben 2 minuten voor tijd nog geen spreker. Dat gaat vast goed komen, maar ik vraag even wat geduld dus. Tot zo.
Tot zo.
Well, Heino, it's here.
So, hello.
Yeah, hello.
Oh, this was a last minute thing. Sorry. I
was a bit nervous, I must admit. But,
yeah, me too. So,
yeah, don't worry. We wait for another few minutes and then we can go along with the lunch talk if that's okay with you.
I'll see whether sharing the screen is working.
Okay.
Yeah, so that will work. I have to.
Yes. Okay, great. I'll do a brief introduction, and after that, you can do your talk, and we have a Q&A afterwards, all within the 12 to 1 time span.
Okay, good. Yeah, I was actually I was doing a film shooting for a documentary.
Okay, on the same subject, I guess.
Same subject, yes. And so I was. This was running out, of course, as usual.
Yes.
It was just coming in a minute before, 5 minutes before.
But they asked you to fly a kite, etc. All kinds of stuff you normally don't do, or was it just an interview?
No, it's okay. It's okay. Yeah, it was.
Okay.
It's still.
And what's this documentary then? Anything we can see as well?
It's on something like Netflix that I didn't know. So,
okay. But perhaps later on we can also see the results.
And yeah, that will be quite good, I think, because they're doing a lot of they're doing gravitational waves. In fact, yeah, as well.
That's nice. Meanwhile, I've started the recording for the present lunch talk, and besides, we have a live stream on NikhefTV. That's a separate channel where people can watch the events without being a participant, because we like to keep this lunch talk program something inside Nikhef mainly. But of course, sometimes we have speakers that are interesting for many people, so we have this stream as well. Let's see, what's the time? It's 12 o'clock. It's a bit slow. I guess it's the weather as well. But then
I think so. I think I wouldn't want to sit in a virtual Zoom lunch talk at this weather, to be honest.
Okay, but nevertheless, we're quite curious for your talk. Let me start with introducing Heino Falcke. Heino Falcke is an astronomer at Radboud University in Nijmegen, as his slide already mentions. And of course, he's a well-known face in the field of black hole photography, you could say. He's doing lots and lots of other stuff as well, but I thought it would be interesting to hear the story of what's in a shadow, black hole imaging. The team with Heino and others have been famous for taking the first picture, you could say, of a black hole, a real black hole in the sky. And they're working on lots of other projects in the same field as well. So there's, I guess, lots of things to tell. Besides that, Heino has also produced a book about his work and himself being a scientist, which I think is really interesting. And I guess it's already out in many languages, but specifically Dutch and English are available, right?
Yes, Dutch, English, German,
right.
Italian will come. Spanish.
Yes, but still, we can't escape it. Like a black hole, we can't escape your book. Right, enough from me. Heino, thank you for being with us. And if you're ready, go ahead with your talk.
Yeah.
I would suggest that we have your talk first, and afterwards we have some time for questions and remarks. So yes. Go ahead.
Okay, glad to be at least virtually with you. I just realized I'm I still have a virtual green screen on, which doesn't make sense. Okay, good. Normally I have a much more professional setup than this one. This was sort of in between things I had to do today. So glad to be at Nikhef again, even virtual. And you all are, aware of how big collaborations work. For us astronomers, this is sort of a new thing, so to speak. That was sort of one of my, I'm involved in also astroparticle physics, and radio astronomy is my official title. And so to me, in the build-up of the entire experiment, it was always clear we had to do something like the particle physicists do. We need a collaboration which, if you want to see the shadow of a black hole, we want to see the event horizon, so to speak, what we need is an integrated team where we do the experiment, the theory, the data analysis, the technology together with one goal, which is quite different from the way we usually do astronomy, because we have an infinite universe out there, and there is, a black hole for everybody. But here there was only more or less one or two black holes and one goal to do. And so this was a big team effort, and getting different institutions together. The Event Horizon Telescope was formed by 13 stakeholder institutions, 4 from Europe, 4 from the US, 2 from Canada and Mexico, and 3 Asian institutions. And Radboud University was one of the original stakeholders. We now sort of hold the board seat for the entire Netherlands. So this is, we've always tried to make sure the entire Dutch community is part of this. And we have now in the Netherlands, we have people from Leiden, from Amsterdam for sure, certainly Radboud, and there's also mainly technical support from Groningen. So that is, and Jive is as well included. And we were all funded by the ERC project, Black Hole Cam, which was the single biggest funding resource, in fact, in the Event Horizon Telescope in the formation. What you see here, that picture is from the collaboration meeting in 2018 in Nijmegen. That's where we really discussed the results and the final image. So that was a very memorable meeting that took place here. Also because of weather, because it was in November and we had wonderful weather, which is the unusual, the surprise in this experiment that sometimes you can have good weather. That was also true for the observation itself. Now, if you want to see black holes, you want to look for the biggest ones and the biggest and closest ones. If you look for the combination, there are many stellar black holes in our galaxy, but they are way too small. There is one big one in our own galaxy, which is Sagittarius A star in our Milky Way, which is 1 million times, it's 4 million times the mass of the sun. But it's only 1,000 times further away than the typical stellar mass black holes. So in that sense, it's 1,000 times bigger than all the smaller black holes, even though they are closer to us. And there is another big black hole, which is here. Let me see if there's another big one, which is called M87, which is the biggest galaxy in our local cosmic environment. This is a central cluster. Multiple black holes have merged to form a big black hole and formed a big galaxy. And so that's again a factor 1,000 bigger than the black hole in the center of our Milky Way, because it was made out of many galaxies in the end. And it's a factor 1,000 further away. So these are the two sources which have the biggest black holes in our neighborhood, and those are the ones you want to look at. And by sheer coincidence, they also radiate near the event horizon at exactly the same frequency. That's just pure coincidence. If you look at the center of our Milky Way, you might have seen this picture, beautiful picture with a Meerkat array. It's sort of a pathfinder of the square kilometer array in the southern hemisphere. And if you go into the very center, in the 70s already, we found that radio source Sagittarius A star in the very central region, a compact radio source that we always suspected is a central black hole. It was first found in Green Bank in the US, but a few months later in Westerbork. So once more, like with the discovery of cosmic hydrogen, the Dutch radio telescopes were just a few months later than the Americans. Now, this time, of course, when it came to the imaging the black hole, we all worked together. So that was not a question of months. As you may know, if you look in the center of the Milky Way, this was a Nobel Prize of Gensel and Gaze last year. You can measure the stars. There's one example of one of the stars orbiting the central black hole. And from this almost perfectly Keplerian, in fact, by now relativistic orbits, you can measure the mass of this black hole. You measure how fast this black hole rotates around the center, and you can calculate how much gravity you need to keep it fixed to the central region. And that tells you they're 4 million times the mass of the sun. So we have a radio source, we have a mass measurement, so you know what to expect. And then you have M87, as I explained. This was also found 100 years ago. You saw this. This is a galaxy, thousands of billions of stars in the center of a cluster of galaxies. And you see this little thing shooting out. In fact, that was found in 1918. Nobody knew what it was. It actually is a plasma jet shooting out from the central region, from a central black hole. And you see the radio emission here on the right side. You see the LOFAR image that was made in the Netherlands. Again, you see the entire region around this galaxy is filled with plasma that all came from the central region. And this is a classical active collective nucleus, a nucleus of a galaxy which shows activity and was suspected to host a supermassive black hole as its origin. Now, you have radio emission, you have a black hole. How does it look like if you have if you are able to see a black hole? And our pictures are dominated by sort of the early phase of quasar research, when we thought black holes were surrounded by thin accretion disk, and that's about it. And these pictures you see in all kinds of movies and in general public depictions. And what you see here is the very first image of a black hole calculated. This is actually just the position of the star going around a black hole on an orbit and how it would be deflected. And so you see this structure. And then, in the late 70s, this was a computer calculation, not one star, but just many dots on a disk surrounding a black hole, and then plotted by hand. And so you see the dark region here, and you see the disk surrounding it, which is folded and changed. And you see it actually, it's not a round thing that you see in the middle. You see, something deformed something. And that purely has to do with the fact that you have the assumption that you're surrounding a black hole with a wall, a thin disk, and that absorbs the light in the foreground. And so that changes the appearance of black holes. And that what you found back in Interstellar in this nice movie, and it's sort of, I think the first part was nice, the second part was a bit crazy, at least for physicists. And but it has this nice rendition of a black hole, which had some problems. It was nicely ray traced, but it misses the Doppler beaming. So one side should be brighter than the other, and it's made out of dust. We know that plasma around a black hole is not made out of dust. It's very hot plasma. It's actually billions of degrees. So when the spaceship is going in towards a black hole, it's hit by little rocks. Always cringe, because that's just if you're hit by a rock with the speed of light, you're going to disintegrate immediately. And in fact, the rocks will hit each other, and they would never survive as a dusty disk. That would be just extremely hot plasma. The only thing that changed, this is NASA a year later. The picture looks still the same, but it's now is red. And I think we played a role in coloring it red in the end. But the basic structure didn't change. Now, when I was thinking about black holes in the 90s about the galactic center, my picture was slightly different, and that was that the black hole in the center of the Milky Way was actually surrounded by optically thin emission, by hot plasma, probably that from the plasma jet shooting out. But you would be able to see, it would be transparent. You would be able to see all the way to the center, and the emission would be extended. And this, in this toy models that we show here, we actually pretended we didn't know any astrophysics. We just were distributing matter in all different directions and asking ourselves, how would a black hole look like? How would the black hole in the center of our Milky Way look like? And one theoretical prediction that we made at the time was that actually millimeter wave emission at 230 gigahertz, sub-terahertz emission, would come from really near the event horizon and would be transparent. And if you do this, you surround the black hole with this plasma. What you'd see is always the same structure. You see this dark region, what we then call the shadow of the black hole, because it's not the black hole that you're seeing. It's just sort of the imprint of the disappearing light that you're seeing here. But what was interesting, and something I hadn't realized 10 years before, but only came out in this work leading up to it, is that independent of how the structure of the astrophysics was, you would always see this shadow, always with more or less the same size. And even if the black hole would be rotating, differently oriented, the shadow would always have more or less the same size within 10%. And so this was a very predictable feature you should be able to see if you look at it with high enough resolution. And I knew at the time already that at least these frequencies, 230 gigahertz, you can get that resolution from a global network of telescopes. That was sort of technologically just in the beginning of developing, but you could see that it would be coming in the next decades. So that in this paper, we said, in this black hole, we should see a shadow that's robust against variations in spin and astrophysics, and we should look at it with a millimeter VLBI. That's an experiment we should be doing. And then we can see literally into a black hole. So how does this work in practice? Just a little bit of a picture here of light rays that are deflected around a black hole. You approach the black hole, then actually the black hole rotates, and it takes a spin with the spin of the spin takes the rotation takes the space with it, and so light will be actually deflected and end up in the event horizon. And that goes back, actually, that picture was already developed by Bardeen in 1916, where he showed that if you have light coming in on parallel orbits, you're shining parallel light on a black hole, it will be deflected. And in fact, there's a certain distance here, I hope you can see my cursor, where light will be bent such that it will go on a circle. And every light that comes in a little bit smaller will actually end up in the event horizon. So if you look at a black hole from within this separation, all your light rays will end up in the event horizon. And that will create that shadow. And that shadow will be actually larger than the event horizon by a factor 2.5. That's the important thing. Now, maybe to explain a bit more, what are we actually seeing? The main thing that you're seeing is actually a blocking effect. So imagine you have a cloud of gas radiating, and you put a dark object in the very center. So what will happen if you look at this gas, you see light from this cloud, but you will not be able to see the light from behind that cloud because it's blocked, okay? And so you'll see a dark region in this very central cloud. And that's exactly the same that you see, this here is an example. You have a kettle in a fire, it's translucent, you can see through it, and you see essentially the dark region of this black hole. A black hole does exactly the same things with a few extra effects, namely the light bending, that the light will not go on parallel lines. It actually you see around the black hole. And so the light that goes around the black hole will be able to pick up even more light as it circles the black hole and that comes towards you. And that will create that light, that bright ring, okay? That will give you more emission at the edge, and it will give you a dark shadow in the very center. And so that's the secret of what we see. Now, of course, you want to do this more accurately in a simulation. And so what you have to do is not just calculate the light bending, which is relatively straightforward to do, but you also need to calculate where is all the matter, where is all the stuff that's radiating. And that requires essentially big supercomputer simulations to solve the plasma flows in curved spacetimes surrounding a black hole. And so you have to solve these equations in a computer, which looks simple. but the computer codes that do that are even more complicated than these equations, and I myself wouldn't be able to do this actually anymore. It's gotten too involved. It's a field of its own to do this, but we can do this. In fact, part of the Black Hole Camp project was to develop a code that's able to calculate plasma flows and light bending around any object in the very center. It could be a black hole. It could be even a non-standard form of gravity. So if you have a theory that's not general relativity, but has different properties or objects that look different, we can calculate how plasma flows around it. Now, if you do all of this, I cut a long story short, you can make these beautiful simulations that we color by hand, not by hand, but by the computer. So the color, of course, is, and so what you see here is a plasma flow around the black hole. What you see in the gray is these plasma jets shooting out, which are very important. And it seems to happen in many black holes that, plasma is, magnetic fields are wound up and shoot out. And you can follow the dynamics of the plasma flow. And you see in the very center, you see this dark region, you see the shadow that's there. Now, this shows the image at all colors at once, so to speak, at all frequencies. If you do a simulation, just focusing in on the center at a certain radio frequency, 230 gigahertz, that's what you would see. And this is a paper that we predicted, that we published in 2016 with Monika Mostybrocka as the first author, predicting how the black hole in M87 would look like if it had a large mass of 6 billion solar masses. You'd see this ring of light from the light bending, and you see the dark region in the very center. So that was actually predicted before we took the data. And the size of this is 10 gravitational radii, 5 Schwarzschild radii is a diameter, and which, in the case of M87 is about 40 microarcseconds on the size. Always compare this to a mustard seed in New York as seen from Nijmegen. Now, in order to resolve this, you need a telescope the size of the Earth. And to do this, we know how to do this. This is interferometry, very long baseline interferometry, a technology that's been around for 20, 40 years, maybe 50. No, 40 years, 50 years. And the first experiments, and so the technology challenge was always to go to higher and higher frequencies to do this. And at 230 gigahertz, where black holes become transparent, you can see the shadow. The first experiments of the galactic center were done actually in Europe, between France and Spain. So this was just 2 telescopes, but it showed the principle, and you could already derive a rough measurement of the size of the black hole in the radio emitting regions, but you couldn't see the structure. Then the American experiment started with Shep Dolman as a lead, 3 telescopes in the US that still couldn't really see the structure, but could get a more reliable measurement of the size. And that really showed that indeed the radio emission is detectable with VLBI and is coming from scales that are comparable to the event horizon. So we built then this big event horizon telescope. That's a book on its own, so as Martijn pointed out. And in April 2017, we had this experiment with 8 different telescopes on 6 different mountains, looking at the galactic center and M87. M87 is published, the galactic center is not yet published. And lo and behold, everything worked well. The weather was beautiful. We had a mixed team. In fact, from the Netherlands, we had people everywhere except South Pole. Though I think the South Pole winter over was someone who had been, I think had studied in Amsterdam even. It's now working at ESA. He's a German. So I think the Dutch were represented everywhere. Of course, not with Dutch. I mean, sort of, Chiaco was Italian, and Sarah Isaoun, who's from originally Algeria, here in Arizona, grew up in Canada and Arnhem. So a very international team, US, European. I was here in Spain together with my Spanish and German colleagues and doing these observations. Now, how does interferometry work? we have to, what we do is replace a big dish with small radio receiving antennas. So the light wave comes in, the dish usually reflects them and focuses them in the focus. That should actually go the other way around. So what happens is you have the lights come in, and if you bring them together in the focus, you get interference pattern. And what we do essentially is we measure the light waves here and here, and the focusing we do later, and the bringing together and interfering the source in the focus we do in the computer. Now, we did this, this is out of, okay, this was after the observations. So you see it was very tiring. This was the ALMA crew. We worked day and night. And in the end, we're able to actually produce this image. Again, this entire story, how we made that image, I'll just show that that movie that zooms into the center of Virgo, and that we presented at the press conference. And we're zooming in by a factor of 10 to the 9 and showing all the radio images of M87 combined. I don't know whether you can still hear me or whether the music is too loud. The mix may change actually. You see the lo-fi image, and then we zoom in to the Hubble image, and then the VLBI image, and then centimeter waves. So you see the jet, and you see the jet, and then you go to the Event Horizon Telescope frequency, and then you see that. That was the image that we made. In fact, that's the latest image, which includes a polarization pattern as well that I explain in a moment. And so that was, in a way, so beautiful because you saw that ring of light and you see the dark region, and it was exactly the size that you would expect for a 6 billion solar mass black hole. And so if you look at this in terms of scales, the size is 100 billion kilometers in diameter. So it really is larger than the planets. This is sort of how far Voyager has gone, and that's really gives you the size of the shadow more or less. So it really is a gigantic thing at 55 million light years distance. We also did a lot of simulations, as I said. And this is a simulation that you see. You see this bright ring here of light. You see sort of a lower resolution light ring that's here, and you see all the substructure that's going on. You see the really dark region in the very center. And we simulated all kinds of black holes under different astrophysical situations. And whatever you do, you see the shadow. And that's the important aspect. The shadow really is a very robust feature that you expect in black holes if you change the astrophysics by a huge amount. Why did we do all of this? We wanted to quantify the error. What is the systematic error that we're making, for example, due to the astrophysics? And that's what we used. And you can see here, there are 3 different models, which are very different astrophysics. They have very different properties of the black hole. One was counter-rotating, the other one is co-rotating. And if you resolve them, if you convolve them with the resolution of the Event Horizon Telescope, you always see the same result. In fact, that's another thing that I started here, inspired by particle physics, because what I learned when doing astroparticle physics, an important aspect was always the detector simulation. You really wanted to have a good simulation of your detector to simulate what you want to see. And we don't have that so much in astrophysics. And what we developed here as part of 2 PhD thesis is a SIMBA simulation package, which really takes, a very detailed, makes a very detailed detector simulation, takes the weather into account, takes the different schedules of the different telescopes into account, simulates what you would get, and processes it exactly in the same with the same data analysis pipeline that we use for making the real images. So that's a real detector simulation that you see here on the bottom. And you see that we recover more or less the theoretical prediction very well for very generic astrophysical cases. And that's just a property of GR that we're probing here. So that's important. Now, then we went back, and this is more recent results. We went back to our previous Pathfinder experiments when we had fewer telescopes, not enough to make images. But once you have an image, you can look at, you can use this as the starting model and ask yourself, what did change, right? in previous data sets. And so even if you just had 3 experiments, you could just still figure out how, was there a ring? Did it change in size and so forth? And the conclusion is that more or less all the data we had previously is consistent with a ring of the same size. And that's important because you expect the black hole ring to be always there. If it's astrophysics, like you have a smoke ring that's blown by the accretion disk or so, it will actually expand, will go out, will change and so forth. But this thing actually is constant because it's sort of determined by the mass of the black hole. What you also can show is, and just is more for the physicists among you, is that the size of that ring is directly related to the time-like component of the metric of space-time. So this is the TT component. That directly goes into the size of shadow. So you measure one particular thing. And it turns out that what the gravitational wave experiments measure is pretty much the same thing. They measure gravitational waves scattered at the photon orbit. And they measure the same aspect of the metric. And you can sort of ask yourself, if we violate GR, general relativity, how would that affect the ring? Well, if you take the best constraints we have from solar system tests of GR, and you go to the second order derivations, the ring could have been in principle factor 500 larger or smaller. So really constraining higher order terms of general relativity. And in fact, we're doing the same, we're probing the same physics as gravitational wave experiments do. And this is here in a paper from Dimitrios Psaltis, putting together constraints on deviations from GR from gravitational waves and from the Event Horizon Telescope. They're essentially covering the same range, but at very different mass scales. Gravitational waves do this for stellar mass black holes. We do it for supermassive black holes. And so GR holds, and that's the important message, GR holds over 8 orders of magnitude when you really probe it in great detail. And so that's really a great complementarity here between gravitational waves and Event Horizon Telescope. And together, really, which theory really holds over 8 orders of magnitudes and gives you exactly the right answer. This is a big thing. One other result I mentioned came out a few weeks ago, just we published a new image, which now on top of it, the polarization structure. So this is the rotation, so the oscillation direction of the light. Now, light can be polarized, and because this light is generated by magnetic fields, that will actually make the light rotate in more or less in a direction, not rotate, oscillate in a direction more or less perpendicular to the magnetic fields. So if you see lines like this, to first order magnetic fields should be orientated on a perpendicular to this. And so this is a very difficult experimentally to measure. And so what you see here are 5 different algorithms that we use that all got the same result. We all split work in different teams and comparing each other. So it's a huge amount of work assuring that the results are correct. And you can infer some basic structures of it. If you have magnetic fields in a plasma, then magnetic fields would actually be torn around and wrapped around the black hole, and it would be sort of in a toroidal pattern. Then you would expect polarization patterns which are like spokes. If you have magnetic fields which are like spokes, then you would expect a circular polarization pattern. What we see is something in between, which means we need something like magnetic fields which can resist the force of the plasma, so that are dynamically important. And the best explanation we have for the polarization pattern is magnetic fields that somewhat stick out of the matter flow. And that fits exactly with our simulations. What you see here is an actual simulation, GRMHD simulations, where you see the magnetic fields like spaghettis, right? And so the magnetic fields are wrapped up like spaghettis here, but near the event horizon, the magnetic fields are actually shoot out and form this plasma jet. That's what launches plasma jets. We can launch jets now in our simulations, and you see how they're sort of at an oblique angle sticking out. And that's exactly the polarization properties we see. So what we're essentially measuring now is the launching of plasma jets near black holes, and it's fitting the simulation, which is quite awesome, actually. Now, of course, the next thing, the final thing we want to see is the center of our Milky Way, the black hole in Sagittarius A star. And this is more challenging. It's actually slightly larger, so in principle, it should be easier. But it's observationally, it's a lower elevation. It's on the southern hemisphere. We have fewer telescopes on the southern hemisphere, so it makes it harder to see. Also, the light has to go through the plasma of the Milky Way itself, because it goes through the Milky Way. M87 comes through us through the empty universe, more or less, while here the light has to go through the entire plane of our Milky Way. And that leads to some form of, you could call seeing or scintillation of radio waves. They're scattered. The radio waves are scattered and blurred. And so depending on how the blurring happens, you could have a ring that looks nicely sharp, or it could be completely washed out. From some experiments that I can talk about now that Sarah Isaoun did here, we think the truth is somewhere in this direction now from lower frequency data. So you should be able to see a ring with some, with some scintillation pattern on top of it. But the other problem is this black hole is a factor 1,000 smaller than M87. So it will actually rotate factor 1,000 faster. In M87, we see this stuff go around the black hole in about a week or a few weeks. In Sagittarius A star, it goes around in 20 minutes. And if you try to image with normal methods, old-fashioned methods, then if you have a single epoch, all you would see you see a little movie if you can look at it carefully. And every 20 minutes, you have some change. In a single epoch, you would just see some ugly structure here. Only if you average long enough, many orbits, you'll be able to get an image. This is something we're working on right now. I can only show you, that's why I'm only showing you data from 2016 in simulations. I could show you more recent ones. We have more data. We have more tools now available than we had in 2016, but I can't show you them because this is something we're working on, will be published hopefully later this year or beginning next year. We'll have to see. We had an observing campaign in 2017, 2018, 2019, 2020. We couldn't observe. 2020 because of COVID, 2019 because of technical issues. 2021, we did observe, and this is what we did. We had actually a telescope in France, NOEMA, that we equipped with our EOC funding. There's a telescope in Greenland that joined, a telescope in Arizona that joined, but the telescope in Mexico didn't join. So what the outcome will be, we don't know, but we'll find out. Probably in a year from now when the data will arrive. We want to go further. We want to expand the network. We want to improve robustness. If a few telescopes, one telescope falls out, we are in deep trouble. And that's why we need more telescopes, and we want to improve the possibilities for Sagittarius A star, because if you want to make a movie of it, there may be 1 or 2 hours where we can do it now, but if you want to do it for a longer period of time, you just need a telescope in Africa somewhere to cover more baselines. And so this is a project we're working on, trying to get the CEST telescope from Chile to Namibia, and that's why we're raising funds now to do this, and also do this with an outreach program that we have going on. In fact, there's this the NOVA Planetarium that we sent to all schools in the Netherlands is now in Namibia. Unfortunately, due to Corona, it can't travel much. It can't travel at all. But it was started as a big success because we want to do science with our colleagues in Africa, and we want to also make sure that the science we do, at least is known and benefits the local population, and help them inspire with astronomy to do science and STEM subjects in school and university. And there's a big, I think, big interest and a big potential also. Really, lots of good and smart students there that need an opportunity. Now, in the long run, we want to go into space. I showed that before. This is a study that we've been doing, 3 dishes orbiting around the Earth, slightly different orbits. And that allows you to fill in essentially all baselines from all directions and allow it to make really sharp images. This here is a movie of a black hole. And this is what you get averaged. And this is what you would get with a space VLBI image. So really, you see all the sharp with no fancy image processing. It's just, just as it comes out of the telescope, more or less. You see really sharp features, details that will tell you about jet launching, allow you tests of gravity to sub% level and so forth. So this is, what we do can just be the beginning. Now, almost even faster. I was so panicked that I would be running over time, that I've been going a bit too quick, but it gives us more time for questions. So I think we conclude a lot. I think we've seen the black hole shadow. That was a clear prediction that we made, a very robust prediction, and all we see really fits the prediction of GR. You can conclude from that the object that we have is smaller than the photon orbit, so it must be smaller than 1.5 Schwarzschild radii. So for all practical purposes, this is the best evidence we have for it being a supermassive black hole. And I think very important not to be underestimated is the fact that if you combine gravitational waves and event horizon telescopes, really GR scales over 8 orders of magnitude perfectly well. And there are models which are alternative theories which have some mass scaling in there, right? So which kick in somewhere in between. And the Sagittarius A star will fill in some gaps in between. So that is a major success of GR. And what are we seeing there? Really, if you trust GR, you're really looking into the event horizon. You can never prove there's an event horizon. You can always get so close to an event horizon. And so the darkness, however, is the darkness from the event horizon. So it's to me, it's still a first order, maybe even second order, prove that there is, an event horizon. There's light bending and an event horizon, both things you need. The polarization measurements we just published, show that there are dynamically important colloidal magnetic fields which can launch jets. And that's quite interesting because in the simulation, what we see is that if the black hole is rotating, they're so close that they're actually able to extract spin energy from the black hole. So some fraction of the energy going these plasma outflows might well be spin energy. And that is an interesting coupling of electromagnetic forces like magnetic fields with GR, with space-time. So that's a very interesting link. In fact, there's a so-called Penrose process where you can actually, by shooting light onto a black hole, you can extract spin energy from it, from the scattering of photons of a black hole. And if you think of black holes as magnetic fields as virtual photons, so to speak, it's essentially the Penrose process we are measuring. And so we think that's happening. We still need to make it a bit harder, but that's certainly something we are probing here. And of course, there's work in progress. As I said, we have the 2018 data that we are correlating and starting to calibrate. So as a further confirmation of M87, and we have the Galactic Center coming up. That's the biggest time sink right now. The data is good, but we have to convince ourselves that what we're doing is right because of all the variability and so forth. So we're running tests and tests and questioning ourselves over and over again before we come out. So it will be quite interesting what we'll be able to say at the very end. And yeah, it's just the beginning. We'll have better images. Just averaging multiple images will actually give us almost order of magnitude improvement in parameter constraints on the black hole, just with what we have. Well, and ideally 1 or 2 more telescopes. We are able to go to higher frequencies, so we're able to make color images to have multiple frequencies. We have more telescopes coming up, Greenland, France, Africa, hopefully, and then eventually space. So while this image is sort of a culmination of 100 years of black hole research, it is also, I think, a step towards a new era of space-time research. We have gravitational waves, we can listen to black holes, we have the Event Horizon Telescope, we can see black holes. We have pulsars, maybe with the SKA, we have black hole pulsars. And so I think space-time research will be something that will take off in the coming decades. And that's it. You mentioned the book, okay, some advertisement at the end. So if you want to read more on this, on black holes, the story of the EHT, and some more thinking about what's beyond, then all of this is in one of these translations. So thank you.
Thank you, Heino, for a great talk, I would say. Thank you so much for going into details and still being able to keep the general view. So thank you for that. I'm sure there's some questions from the audience. So if you have a question, you can unmute. Beatrice, you're already raising your hand, so go ahead.
Yes. Well, I would like to know the following. In gamma rays, I mean, using in observations with gamma rays, it's known that the plasma in the vicinity of black holes and also pulsars is a lot of it is matter antimatter, so electron-positron plasma. This is very easy to see in gamma rays. So my question is, if in radio frequencies you can also distinguish, no? If you are seeing ordinary proto-electron plasma or you see electron-positron plasma.
It's a very good question. It's a much harder to answer in radio. In fact, that's a debate raging in radio astronomy. Are these jets? Are these electron-positron pairs? Or are these normal proton-electron plasma? Now, what I can tell you is, at least in our simulations, we can recover all the properties with just the ordinary plasma that's in the accretion flow, including the polarization and so forth. You can calculate how many pairs are being produced, either by a gap model like you have in pulsars and so forth, or by proton-proton or proton-gamma collisions. We don't know of a process that produces enough pairs to produce all the radio emission with pairs. So my strong prejudice at this moment is that the predominant contribution to the radio emission is from normal plasma. But I know there's some people, some of my colleagues have different opinion, some of them, but I don't think they can make a very strong case for a strong pair contribution. I would not rule out that there are pairs present, right? That's, but and also in gamma rays, at least if I look at the continuum gamma emission of AGN, I'm not sure you necessarily need pairs there.
Well, one can see the pairs because of the annihilation. The line 511,000 electron volts. So it's
but you don't see that. Yeah, yes, I agree, but you don't see it in the plasma jets directly, for example. And so when it comes to the plasma jets, I don't think that there's strong evidence for pairs yet.
No, but also, as far as I know, people do not understand very well why this, which are the mechanisms. As far as people do not understand very well the mechanisms either.
But it's certainly a very important question. Yes.
Thank you, Beatrice, for raising an important point. Perhaps even food for thought and new experiments, who knows. We have a few questions. I noticed Leo Wiggers had a question, and then we have some more raised hands. So Leo, if you're there, go ahead.
Yeah, I saw that you are targeting now the black hole in the Milky Way, but are there not any other easy targets like M87?
Yes, they are, but they are not easy. For two reasons. A, M87, M81, for example, is factor 10 fainter. It's also factor 100 further away. So it's actually too small to be seen. So if you want to see more black holes, you really have to go to space. It just, the Earth is not big enough. But if you go to space, there could be many, many black holes that you could image.
Okay, we just have to wait for that then. Let's go to Joris van Heiningen.
Yes, thanks Heino for this nice talk. Really cool to see all these images and movies of stuff that made it come alive, let's say. One of those movies where you showed this is made with different frequencies, and you saw the red and the gray. I saw these kind of gray pulses in image. Well, it looked like pulses or so.
Yeah, but
that's like a lighthouse effect.
Yeah, that was essentially because the jet was sweeping towards you, and you saw a blob coming into your camera. Yeah,
I thought so, and that's nice because it's a short question, and I can take the second one. Yeah. I saw that you're going in space with the satellite, but there's a lot of renewed interest in going to the moon. Also, so I'm a gravitational wave, and I want to go to the moon to use the moon as a bar detector. But is there not something to gain for you guys to put like a dish on the moon?
If you want,
very nice.
I'm with you, and I'm one of the people, proponents who've been saying we need to go to the moon to do radio astronomy there. That was mainly to do Big Bang cosmology at low frequencies in the shielded regions behind the moon. And also being away from the ionosphere. Now, for this kind of work, you could place a single dish on the moon. That would be possible. The baseline would be a bit too large. So the advantage of having them closer to Earth is that you have them, and 2 or 3 of them, that they together form. You measure all separations and all orientations. And that gives you a much better image quality.
Is it, in other words, the triangle becomes a bit too flat?
Yeah, it's not a triangle, it's just one line, right? You don't have a triangle.
No, but I mean with all the other ones. Yeah, okay. Anyway, I think we're
you would have,
thing.
If you have more free-flying telescopes out there, then you could combine it. You could have one on the moon, one on the Earth, and then the other ones in space. But then it's actually, in the end, more efficient probably to do it completely in free space.
Okay, thank you.
So the case is better for low frequency than for high frequency on the moon. It's actually very good. I mean, in fact, I know we just yesterday had a meeting with ESA for their moon lander, and a radio experiment is on their, definitely on their in their books.
Okay.
See you on the moon then.
Yes. Well, I could mention that Joris actually will be doing a lunch talk soon about a special project he's planning, or perhaps fantasizing about, doing on the moon connected to gravitational wave detection. So stay tuned for that. Let's go to Stan.
And you should contact us, because we have a topical team now which addressing some of the lunar lander stuff. So it's very timely now.
Please do. Stan, go ahead.
Yeah, I know. Fantastic talk. Thanks. And it's good to see. I was a few minutes late, and so my question is a little bit related to maybe what Leo was asking you. What are the requirements in order to be able to make an image of this black hole? And I wonder, you talk here in your last bullet on epochs, on movies.
Yeah.
If you fantasize about future measurements or future events, do you consider, for example, with a gravitational wave detector, being able to predict a double black hole system to be coalescent, and that you would be able to observe that event?
That, of course, would be, not even the platinum thing. It would be whatever. I mean, this is you
fantasize a bit.
Absolutely. There are some practical problems. The first one is these both would have to emit at the right frequencies. They would need to be bright enough, and so AGN activity is somewhat limited. So you need to have very sensitive telescopes, and it's not always the same frequency, right? It really depends on how much matter is falling onto the black hole, which frequency to choose. The fact that we can do M87 and Sagittarius A star with the same experiment is just pure coincidence. It just, I mean, God was gracious to give us those two sources. They were just big enough to be seen from the Earth at the same frequency, just before the atmospheric window was cutting us off. right? So it was just, you know, at the edge, literally, in all respects, and completely. There's no physical reason that this should have been possible. And then I think you definitely would need really a major space array, and probably not even the one we're talking about now. Maybe one that comes thereafter, if one. But you know, you can be lucky. I mean, to be honest, I mean, the gravitational wave people, you know, we're lucky with their first event, and we were lucky with our first experiment. So maybe if you put our luck together, maybe that it will work out.
But okay, but so a little bit more than downscaled. What sort of movies can you make? What is the
good point? Like M87, it will change from week to week, right? Yeah. So what I'd love to do is to make really an image every week or every other week, and just continuously follow this one. And so that requires a different operational setup. You just need more telescopes, because one telescope will go in and out, the weather will be bad and so forth. So that was one of the reasons. That's really one of the main reasons why we want to have this Africa telescope, because it'll give us more independence. So if Chile, for example, we're not going to get ALMA all the time. You know, this big, massive telescope. But if we have a telescope, we have a telescope in Africa. It actually can replace the one in the ALMA telescope in Chile.
But you need roughly around a week or so to create an image.
No, you need to observe. You only need one night.
Okay.
And then you want to do one night every week, so to speak, for a couple of weeks. Then you can really trace the plasma going around. Okay. And for the galactic center, the stuff goes around in 20 minutes. It's much harder, but then again, if you have more telescopes, you could, you have more image information, and with clever image processing, you could also try to follow it. So I think, and we would have then information on very different timescales with different quality, which also is quite nice. So that's in principle possible, but it requires more stamina, and it's much more, it's probably as much work as the last 10, 20 years to get this going, and stable funding to do this. And that's, as you know, is a problem in some of these experiments.
We all need.
I'm completely broke right now, just to be quite frank. Right, yeah. So okay. I can't contribute to this experiment at this moment, except for one.
We'll start a crowdfunding then.
Yeah.
Okay.
Well, it will not be enough. So.
A silly question from my side. You keep mentioning one bright night, but you're doing radio astronomy, right? So why do you need nights?
Because we are millimeter waves are affected by humidity. They are the size of In fact, this is the same technology used to look through your clothes at the airport, but it doesn't go through your body really. And so clouds impinge the radio wave. So you need, and the nights are typically dry and colder and better. You could observe during the day. That's true. It's just the humidity is usually higher, and some telescopes don't work well during the day.
Okay.
But it could be done during the day. That's true.
Yes. Well, interesting, but I always see astronomers working at night because it's dark and you can see the stars. But there's also other reasons for doing astronomy at night, right?
Yeah.
Okay.
But it's not as important as for optical astronomy, right? So yes, for example, the Mexico telescope is a big steel dish, and as the sun rises, it deforms and so forth. Yeah, and right. We'd have to improve the pointing model, and they have many other problems as well. So sometimes it's details, but yeah.
Okay. Well, we have a final raised hand from Stan again, right? Or is this the old hand? It's the old hand. Okay. Any more questions? Because we're nearly 1 o'clock, and traditionally that's the end of our lunch talks. Any more questions? I don't see them. So with that, I'd like to say a big thank you to Heino again for this really amazing and interesting talk. Very inspiring, I would say. And I love the connections you made to the field of particle physics, and some of the insights that came from combining, for instance, gravitational wave detection and this research you told us about. So great field. Nice to be neighbors.
It's definitely true that certainly I learned from the astroparticle physics in how to set this up, and it takes a while until sort of that the way of you do things, go over into other fields. But
Right.
that certainly was an important lesson
Okay.
learned.
Well, thank you again from all of
Thank
us
you.
at Nikhef, and hopefully we'll see you soon live again somewhere in our
Yes,
new
I
building,
hope.
for instance.
Yes.
Let's hope for that. Next week we have a lunch talk. I have put up the slide from Frans van Lunteren. He's a historian of science, and he is talking about the eternal question, I would say, what makes physics tick? He has some mechanisms as to why physics can be so successful in the past few centuries. So join us again next week on Wednesday from 12 to 1. Lunch talk at Nikhef. Be welcome and stay safe. See you then. Bye-bye.
Thanks. Bye-bye.
Bye.
David, ben je er nog? Ik geloof het wel, hè? Ja.
Ja,
Volgens mij ging het helemaal goed dit keer.
ja hoor, er is. Ik zal de stream even stoppen.
Ja? Kun jij zien of daar mensen naar kijken ook? Dat weet ik helemaal niet.
Even kijken.